Hello everyone and welcome to the official YouTube channel for Wayne State University's chapter of the Tau Beta Phi Engineering Honor Society. My name is Austin Heitzman. I am back yet again with another linear algebra tutorial video as promised. We are knee deep in chapter 3 and today we are going to be looking at section 3, which covers basis and dimension. I don't know about you guys if you are currently in an elementary linear algebra class, but my instructor very recently made it quite clear to us that this is sort of the point where people kind of start falling off and not understanding. And as I am starting to see, that is largely because this really draws in a lot of what we've already covered. Like I've been saying through this entire series, this is definitely one of those classes where you need to understand every step of the way because it all builds on itself, right? So we're kind of in the middle of the course, and we really need to make sure that we're still remembering everything that we covered in the first half, as you can probably even see already based on the first section of what we're covering here. So if you are feeling stuck or lost on any previous concepts, we do have pretty much every section of the course posted on our YouTube channel already. I highly recommend you go back and review those if you need to, or just ask elsewhere for help. However you do it, I don't care how, but you should do it. You reach yourself a thank you. Alright, so without further ado, let us begin going over section 3.3. And we're going to talk first revisiting the idea of linear independence. Like I said, this is something we covered a little while ago. If you're shaky, go ahead and revisit it. But I'm going to assume that you are all on the same page, on solid ground here. So let's look at this again. Basically, since we have already talked about things like vector spaces and like sets within a vector space, we can now apply the idea of linear independence and linear dependence to vector spaces. Doing so will help us build the foundation we need to understand what a basis is, right? So let's do that. Basically, I have the definition written out. So we have a set S containing whatever vectors it has. Within a vector space, V, we can say that that is linearly independent if the only solution to this linear combination, another idea we talked about in the past, is the trivial solution, which is all of the scalars equal each other and they all equal 0, right? Conversely, if the equation does have a non-trivial solution, so if these scalars do not equal each other, then the set is linearly dependent, right? This is exactly the same thing as the idea of independence and dependence when it came to individual sort of sets of vectors, right? But now we can apply that to the idea of vector spaces, which is pretty cool. So why does this matter? Well, this will definitely help us talk about what the basis of a vector space is. So subset, call it B, of a vector space V is a basis for V, provided a couple very important things. The first thing is that V is linearly independent, and the second is that the span of V is equal to the vector space. Yet again, we have another concept that we talked about in the past that is coming back to bite us. So hopefully it's not too sharp and we are prepared. So this seems good on paper, right? Linearly independent and its span is the vector space, but it's gonna really help us out if we can ground that into what that really means, right? So we can pull a couple ideas out of this. The first is that the vectors in B, say it generates the entire space. And this essentially means that the vectors in B are the building blocks of V. Nothing in V lies outside of the reach of B. And this makes sense because it's linearly independent, right? I mean, remember when we talked about independence, really quick, terrible sketch here, but that basically means that every single spot in this range can be reached via a linear combination of these basis vectors, right? So that's another concept that we've seen in the past that's going to be really helpful to have in our back pocket. The other thing that this can mean, going off of that, is that there are no missing directions, right? So we'll see this in a minute, but basically, like, if the space is something like, say we have like R3, right? The basis needs to be R3. We can't have it be R2. That wouldn't make sense because that would essentially be missing an entire direction, which goes back to what we just says, because it needs to generate the entire space. There can't be any spots that aren't hit, right? And the third thing that I want to mention that is kind of like a reiteration of this last point, but it's worth bearing in mind again. You can essentially say that B is a spanning set for V. And the reason I point this out is because this is like the official terminology. You know, you can say that B spans V. So when you hear that in your text, all that really means is what we just said, right? There's no part of V that is not within B's reach, right? So now that we have an idea of what a basis is, we can kind of touch on the idea of the standard basis. Basically, so if you think about it, like a vector space can have any number of bases, really, but there are going to be some that are easier to work with than others, and some we've already even seen, actually, way back at the very beginning. So if you remember, for R superscript n, we had a whole video again talking about vectors in R superscript n, and if you'll remember, that included the idea of these like E1, E2, going all the way to En, and that what looks like in practice is going to be the first cell is 1 and the rest are zeros for E1. For E2, same idea, all the way down, kind of like a little step stairs, until the last element is 1, right? This is the standard basis of R superscript n, right? And you can substitute any number in for n, it's still going to be the same. So in this way we can say standard basis for R of n is this chain. Alright, we have our first standard basis. Now, in the same vein, another example is the space of two-dimensional matrices, right? So this is going to look really similar, right? And especially, it's going to look very similar if you remember how we can sort of pull apart matrices to look like vectors, right? So just a little sidebar, I just want you to see this. So if we have a two-dimensional matrix like this, we can write that as a vector if we need to, as this guy right here, right? Now, this is going to have 4 little cells, right? Which would mean that if this were in terms of vectors, we would be looking at R4, right? So, think about how we just defined the standard basis for a vector space, right? It's basically this kind of stair step. It's the diagonals of a 0 matrix should be 1, right? Its trace. So, I'm sure you can kind of piece together what that would mean for the 2-dimensional matrices, right? Because how would we make the second component of this standard basis? It would look like something like that, right? Until we got to this last element being 1. So, in that frame, we can now write this out. Look like 1. Alright, so that is going to be the standard basis for the space of 2-dimensional matrices. And if you're still a little lost on how I went from here to here, highly recommend you just pause the video, take a sheet of paper, and draw it out. You know, like actually take these matrices, write them in terms of a vector, and see that it really does line up. I'm not going to rewrite it like that, but we'll just say standard basis. You can box this guy in. And there's one more space that is pointed out in the book, something we haven't worked with as much, but it is really starting to slowly take center stage, so it is worth pointing out. And that is going to be the set of polynomials with degree of n or less, if you'll remember that from a past video. And this is very similar, right? Basically, we want the bare bone structure of a base, right? And since we're already getting well into this video and we still have a lot together, I will leave it as an exercise for you to kind of unpack why this is. But we can state with certainty that for the set of polynomials of degree n, its standard basis is going to look like this. Oh, not R, B. Alright, so basically standard basis, we just want like the easiest way to access all of the other points in the vector space, right? Very, very similar to unit vectors, if you remember about that. In fact, what are unit vectors but the standard basis of R3, right? So really this is all things that should be familiar and kind of ring bells to you, but it just kind of takes a little bit of kind of getting your hands dirty with it. So beyond that, now that we know what a basis is, we need to look at like the practical aspect of how to determine whether a set is a basis. And I bet you, based on what we've done in the past, these videos, you can guess that it is going to have to do with row reduction. Yay! Familiar territory. Personally for me, I mean, I really tried to hammer home how to do row reduction very early on, and so now that it's coming up every single time, it's like, okay, cool, I know how to do this. Let's go. So, as you can see from the list of stars here, row reduction is going to be the second step, but the first is basically to form an augmented matrix. right? So, and we are going to do our example as a problem like this. So I won't get too far into it right now, but basically if you're given like a set of vectors, right, you can use those to form a matrix and then augment it with the target, right? We will see that later on, I promise. And basically, we can just use the definition of a basis to determine whether it is, right? So if span of the proposed basis is B, and B is linearly independent, the set is a basis. And this is like an exclusive if, right? So if either of those things are not true, you do not have a basis, right? Now similarly, if you want to find a basis, if you're not given like some sort of target that you need to plug in, simply append a variable vector to the set. Right, and again, this is all things that we've done before, right? So it's like a lot of new terminology, but the heart of it, the concept, is really very similar to what we already know. So like I said, we will do our example problem covering something like this. Before we do that, though, we do need to mention what a dimension is. And since this is a pretty straightforward concept and not something that's covered too much in like the problems that this section gives, I just wrote out some notes and we're going to talk about it for a second, but it's very straightforward. Basically, the dimension goes off the idea that any basis of R superscript n must have n vectors, right? We just talked about why, if you have less than that, then there's going to be a quote-unquote missing direction, right? Because of this, that number n is the dimension of R superscript n. Basically, the dimension is just how many vectors does your basis have, right? And we denote it using this terminology right here, if V is the vector space. Like I just said, this represents the number of vectors in any basis of V, right? And once again, this makes sense because if a supposed basis has less vectors than n, it is not going to be linearly independent. It's going to be dependent because you're going to have a free variable, right? All of these ideas are starting to come together. It's really nice. And since the textbook mentioned it, I figured I would also throw out there that V there's a couple different kind of dimensions it can be. It can be either finite or infinitely dimensional. The homogeneous system, x equals 0, is finite dimensional. Just so you have a reference. This isn't really something that has come up, at least for me, so I'm not too worried about covering it in detail. However, if it comes up later on, we will revisit the concept. Right now, I just really want to focus on getting you guys working through an example. So, the one that I've picked out looks something like this. We're going to determine whether this set S is a basis for the vector space V. The vector space we're looking at is R3, and this is the set of vectors. Now, immediately, we know that it is at least a contender, right? Because again, we have R3, we have 1, 2, 3 vectors. So we know that at least it has the potential for being a basis. Like I said earlier when I was laying out kind of how to solve these, sometimes you're given like a sort of target, right? Determining like whether the basis would fit with this. In this case, we're just asked to see whether this is a basis. So we're gonna need one of those like what I call variable vectors. I don't really know if that has like an actual technical name, but that's what I'm going to call it. I know that it's R3, so I'm going to say that this vector is going to be A, B, and C. And once we put all of these into a matrix, we're going to augment it with this, right? This is going to be what we append as the sort of solution to it, right? So let's do that. We have this first vector is going to be the first column, second vector is the second column, and the third is the third. If you will remember, for augmented matrices, we just draw this line down the middle and add our A, B, and C from there. Like I said, we are going to do some row reduction yet again. This is probably the billionth, cajillionth time we have done this in this series already, so I'm not going to do too much detail into this. However, I do recommend you just take some time to actually work it out for yourself. It is excellent practice. Alright, I have just saved everyone about 5 to 10 minutes of their lives because I'm working slowly tonight, so you're welcome. But basically, I have just done the row reduction, and as you can see, I did not take this all the way down to reduce row echelon form, which, just for a refresher, that just means that these are still not 0, right? You can see. However, we don't really need to do that for the scope of the question, right? It's just asking, like, determine whether S is a basis. We're not asked to, like, find anything very specific about this, just like a yes or no and a why, right? But what really matters is that each row has a pivot, right? Those pivots are 1. So this becomes pretty easy, right? We have determined that it is linearly independent. And as such, the span of this is going to be R3, right? Now, what does this mean? Well, we can pull this all together and say that S is linearly independent, and the span S is R3, and looking back, our vector space is also R3 as well, which means the span of B equals V, as we heard earlier. So S is a vector space. Oh, sorry, it is a basis. Wow, I'm really working weirdly tonight. Alright, so that's pretty much it. As you can see, this really just has to do with a lot of the things we've already worked on before. It's just a matter of pulling this all together with some new terminology. And yeah, just make sure that you're really practicing this as much as you can, really getting it under your skin. If there's any like terminology that isn't fully sticking, look it up. Actually like do some digging, do some research, see what all of this really means and how it connects to each other. And if you do that, then you're going to be in much better shape because of it. So thank you for sticking with me and bearing with me tonight. As you can see, I've been a little bit all over the place, but I appreciate you. Hopefully this has helped clear up some of your questions. If you do need a refresher on past concepts, like I said, please be sure to check out the rest of our channel. We've got pretty much the rest of the course that has been covered so far already posted, with more to come. With that in mind, please like and subscribe if you are interested in following me to the end of this. We're almost there, home stretch, almost. Additionally, our channel also has plenty of other STEM-based tutorial videos, things for like math courses, engineering, anything that you really need to succeed. So be sure to check that out. I will be back again with info for section 3.4. Until then, happy studying.